There's a black hole at the center of our galaxy that weighs as much as 4 million suns. And right now, as you listen to this, we're all orbiting around it at 514,000 miles per hour. You can't feel it. You never will. But every star you've ever seen, every constellation, every point of light in the night sky is caught in this ancient cosmic dance, spinning around a darkness so dense that not even light can escape it. And that spinning has been happening for over 13 billion years. If you're new here, welcome. This is a space dedicated to exploring the universe's most fascinating mysteries in a calm, meditative way. A place where curiosity meets tranquility, where knowledge becomes a gentle companion as you drift toward sleep. If you find value in these journeys through wonder, I'd be grateful if you'd subscribe and turn on notifications. It helps these explorations continue. Tonight, let's turn our attention upward, to the river of light that ancient peoples saw stretching across the darkness. The Milky Way, our home. A galaxy so vast that everything you know, everything humanity has ever experienced, every story ever told, exists in just one tiny corner of it. The Milky Way contains somewhere between 100 and 400 billion stars. Think about that number for a moment. Even if you counted one star every single second, without stopping to sleep or eat, it would take you over 3,000 years just to count to 100 billion. And yet, all those stars, every single one, are so far apart that if you could somehow travel at the speed of light, it would still take you 4 years just to reach the nearest one to our sun. Which brings us to something remarkable about scale. If you shrunk the Milky Way down so that our entire solar system, everything from the sun out to Pluto, was the size of a single quarter, the galaxy would still be larger than the entire United States. We live in a structure so immense that human minds didn't even realize it existed until less than 100 years ago. For most of human history, we thought the Milky Way was the universe. Every astronomer, every philosopher, every person who looked up at the night sky believed that the fuzzy band of light stretching overhead represented the entirety of existence. It wasn't until 1924 that Edwin Hubble discovered the truth. Those small, cloudy patches we could see through telescopes weren't nebulas inside our galaxy. They were entire galaxies beyond it. Hundreds of billions of them, each containing hundreds of billions of stars. But let's return to our home. The Milky Way is shaped like a flat disk with spiral arms, and we live about halfway out from the center, in a minor arm called the Orion Spur. If you could step outside our galaxy and look at it from above, it would resemble a vast cosmic pinwheel, with elegant arms spiraling out from a bright central bulge. Those arms aren't solid structures, they're density waves, regions where stars and gas temporarily bunch together before drifting apart again, like cars slowing in highway traffic. And here's where it gets even more interesting. Those spiral arms are birthplaces. Inside them, in vast clouds of gas and dust, new stars are being born right now. At this very moment, somewhere in the Milky Way, a cloud of hydrogen is collapsing under its own gravity, heating up, beginning to glow. In a few million years, it will become a full-fledged star, burning bright in the darkness. Our galaxy creates about 7 new stars every single year. Consider for a moment what that means. The Milky Way is 13.6 billion years old, nearly as old as the universe itself. For almost the entire history of time, our galaxy has been making stars, generation after generation after generation. Some of those stars still burn today. Ancient red dwarfs that formed when the galaxy was young and will continue burning for trillions of years to come. Others lived fast and died young, exploding as supernovas and scattering their remains across space. And those remains became us. Every atom in your body heavier than hydrogen was forged inside a star. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it came from stars that died billions of years ago. Stars whose explosions sent those elements drifting through the galaxy until they eventually gathered together to form our sun, our planet, and you. We are, quite literally, made of stardust, which connects to something profound about the nature of galaxies themselves. They're not just collections of stars, they're recycling systems. Stars form from gas clouds, live their lives, then die and return their material to space, enriching it with heavier elements. Those enriched clouds collapse to form new stars, which eventually die and enrich the gas even further. Each generation of stars contains more heavy elements than the last. Our sun is a third-generation star, born from the remains of at least 2 previous generations. The very existence of planets like Earth, rocky worlds with iron cores and oxygen atmospheres, is only possible because of this cosmic recycling. The Milky Way is spinning, but it's not spinning like a solid disk. Different parts rotate at different speeds. Near the center, stars orbit faster. Farther out, they move slower. But here's the mystery. They don't move as slowly as they should. When astronomers calculated how fast outer stars should be orbiting based on the visible mass of the galaxy, they found something impossible. Those stars were moving way too fast. They should have been flung out into space long ago. The only explanation is that there's more mass in the galaxy than we can see. A lot more. In fact, about 85% of the mass in the Milky Way is completely invisible. It doesn't emit light, doesn't absorb light, doesn't interact with normal matter in any way we can detect except through gravity. We call it dark matter, and we have no idea what it is. It's one of the deepest mysteries in all of science. The galaxy you're orbiting right now is mostly made of something we cannot see, cannot touch, cannot understand. And alongside this invisible scaffolding of dark matter, there's something even stranger woven through the galaxy. Vast regions of nothing. The space between stars isn't truly empty. It contains gas, mostly hydrogen, spread incredibly thin. On average, there's about 1 atom per cubic centimeter of space. For comparison, the air you're breathing contains about 10 billion atoms per cubic centimeter. The galaxy is, overwhelmingly, emptiness. But that emptiness isn't silent. Radio telescopes can detect emissions from the hydrogen gas between stars. And when astronomers map these emissions, they can trace out the spiral structure of the galaxy. That thin gas, spread across thousands of light years, hums with a frequency of 1420 megahertz, the natural resonance of hydrogen atoms. It's the most common signal in the universe, the background hum of existence itself. This leads to something equally fascinating about how we perceive the Milky Way. When you look up on a dark night and see that band of light stretching across the sky, you're looking at the combined glow of billions of stars too distant and too faint to see individually. You're looking edge-on into the flat disk of the galaxy. But here's what most people don't realize. You're only seeing a tiny fraction of it. The band of light you can see with your naked eye represents perhaps a few thousand light years of depth. The galaxy extends 100,000 light-years from edge to edge. Most of it is completely invisible to human eyes, hidden behind dust, dimmed by distance, or simply too faint to register. Ancient peoples didn't know they were looking at a galaxy. The Greeks thought it was a river of milk, spilled across the sky by the goddess Hera, hence the name Milky Way. The Romans called it the Via Lactea, the road of milk. In Chinese astronomy, it was the Silver River, separating two lovers who could only meet once a year. Cultures around the world saw it and invented stories to explain it, but none of them guessed the truth, that they were seeing their own cosmic home from the inside. The view we have of the Milky Way is unique to our position within it. If Earth were located in the central bulge, the night sky would be spectacular. Hundreds of bright stars packed close together, some so near they would cast shadows at night. But radiation levels there would make life nearly impossible, and the frequent supernova explosions in that crowded region would sterilize any nearby planets. We live where we do, in this quiet suburban arm of the galaxy, precisely because it's safe. Boring, perhaps, by cosmic standards, but safe. Yet even here, in our peaceful corner, the galaxy's history has shaped us. About 2.6 million years ago, a nearby star exploded as a supernova. It was far enough away not to destroy life on Earth, but close enough that its radiation swept through our atmosphere, stripping away some of the ozone layer and potentially contributing to climate changes that affected human evolution. We carry the marks of that explosion in deep-sea sediments, where isotopes of iron-60 settled, isotopes that could only have come from a stellar death. The universe has touched us more directly than most people realize. And here's where the story deepens. The Milky Way hasn't been alone throughout its history. It's been eating other galaxies. Right now, there are dozens of small dwarf galaxies orbiting around ours. And slowly, gradually, we're pulling them apart and absorbing their stars. The Sagittarius dwarf galaxy is currently being torn to shreds by the Milky Way's gravity, its stars forming long streams that wrap around our galaxy like ribbons. In a few billion years, it will be completely absorbed, its stars becoming part of the Milky Way. This connects to something profound about galactic evolution. Galaxies don't exist in isolation. They grow by consuming their neighbors. Our galaxy has been doing this for billions of years, growing larger and more massive with each meal. The stars in the Milky Way's halo, the sparse regions surrounding the main disk, many of them likely came from smaller galaxies that were absorbed long ago. They're refugees from destroyed worlds, now calling our galaxy home. But the most dramatic meal is still to come. About 4.5 billion years from now, the Milky Way will collide with Andromeda, our nearest large galactic neighbor. Andromeda is currently 2.5 million light-years away, but it's moving toward us at 250,000 miles per hour. The collision will be spectacular, not violent, because the space between stars is so vast that virtually no stars will actually hit each other, but transformative. The two galaxies will merge over billions of years, their spiral structures destroyed, their stars mixed together into a new elliptical galaxy that astronomers have already nicknamed Milkomeda. By then, the Sun will be nearing the end of its life. Earth will likely be uninhabitable, and if any of humanity's descendants still exist, they'll witness a night sky filled with the combined light of two colliding galaxies. But that's far in the future. For now, for the next few billion years, the Milky Way remains stable, spinning quietly through the darkness. Which brings us to consider the center of the galaxy again, that supermassive black hole we're all orbiting. It's called Sagittarius A star, and it's surprisingly quiet for something so massive. Most supermassive black holes at the centers of galaxies are actively feeding, pulling in gas and stars, heating that material to millions of degrees, and creating brilliant beacons of light called quasars that can outshine entire galaxies. But Sagittarius A star is dormant, barely feeding at all. It's a sleeping giant at the heart of our cosmic home. Yet we know it's there because we can watch stars orbiting around it. There's one star, designated S2, that completes a full orbit around the black hole every 16 years. Astronomers have been tracking its motion since the 1990s, watching it swing around an invisible point in space at speeds approaching 3% the speed of light. The mathematics of its orbit tells us precisely how massive the black hole must be, even though we cannot see it directly. And that black hole, massive as it is, represents only a tiny fraction of the galaxy's mass. The Milky Way weighs somewhere between 1 and 1.5 trillion solar masses, meaning it has the mass of more than 1 trillion suns. Most of that mass is dark matter, invisible and mysterious. But even the visible portion, the stars and gas and dust, represents more matter than the human mind can truly comprehend. This vast structure, this cosmic city of stars, moves through space as a single unit. The Milky Way isn't stationary. It's falling toward the Virgo cluster, a massive collection of galaxies about 65 million light-years away. We're traveling at about 1.3 million miles per hour toward that cluster, pulled by the gravity of thousands of galaxies gathered together. And the Virgo cluster itself is falling toward an even larger structure called the Great Attractor, a gravitational anomaly so massive that it's pulling our entire region of the universe toward it. We're falling. And we've been falling for billions of years. And will continue falling for billions more. The universe is not static. It's a vast dance of matter in motion, galaxies streaming through space like rivers flowing toward an ocean, all of it governed by gravity, that weakest and yet most far-reaching of forces. But let's bring our attention back to something more immediate, more personal. The Milky Way has a heartbeat of sorts. Every 200 million years or so, our solar system completes one full orbit around the galactic center. Astronomers call this a cosmic year. The last time we were in this position in our orbit, dinosaurs ruled the Earth. The time before that, the first reptiles were just beginning to crawl onto land. In the entire history of complex life on Earth, our planet has completed only about 23 orbits around the galaxy. And during each of those orbits, something remarkable happens. Our solar system doesn't follow a perfectly circular path. It bobs up and down through the galactic plane, like a horse on a cosmic carousel. Every 30 million years or so, we pass through the densest part of the galactic disk, where spiral arms are crowded with stars and gas clouds. Some scientists have proposed that these passages might be connected to mass extinction events on Earth, though the evidence remains debated. The galaxy, distant as it seems, may have directly influenced the evolution of life on our planet. This connects to a deeper truth about our relationship with the Milky Way. We don't just live in the galaxy, we're of it. Every element in your body was forged in the nuclear furnaces of stars. The energy that powers your thoughts comes ultimately from the sun, which formed from a cloud of galactic gas. The very existence of Earth, with its stable orbit and protective atmosphere, is a consequence of our location in the galaxy, far from the dangerous center, in a region where heavy elements are abundant but catastrophic events are rare. The more you think about it, the more profound it becomes. You are an arrangement of atoms gathered from across billions of years of galactic history, temporarily organized into consciousness, capable of looking up at the night sky and recognizing your cosmic home. The galaxy made you. And now, for a brief moment in cosmic time, you're here, aware, able to contemplate the vast structure you're part of. There are stars in the Milky Way that have planets orbiting them. We know this now. Telescopes have detected thousands of exoplanets, worlds circling distant suns. Statistical analysis suggests there might be as many planets as there are stars, perhaps 100 to 400 billion worlds scattered throughout the galaxy. Many of them are nothing like Earth, gas giants larger than Jupiter, scorched rocks orbiting too close to their stars, ice worlds in eternal darkness. But some might be just right. Current estimates suggest there could be 40 billion Earth-sized planets in habitable zones around their stars in the Milky Way alone. 40 billion worlds where liquid water could exist on the surface, where the temperature is neither too hot nor too cold, where life, if it arose, might have a chance to flourish. And if even a tiny fraction of those worlds developed life, and if even a tinier fraction developed intelligent life, we might not be alone in this galaxy, which raises one of the most profound questions humans have ever asked. Where is everyone? If the galaxy is so old, if there are so many potentially habitable worlds, why haven't we detected any signs of alien civilizations? This question, known as the Fermi paradox, has no certain answer. Perhaps life is extraordinarily rare. Perhaps intelligent civilizations destroy themselves. Perhaps they're out there, but the distances are simply too vast for communication. Or perhaps they're here, watching, waiting, and we simply haven't recognized the signs. The galaxy is vast enough to contain all these possibilities and more. It's a structure so immense that humanity, with all our technology, has barely begun to explore it. We've sent probes beyond our solar system, but they won't reach even the nearest stars for tens of thousands of years. We've built telescopes that can peer across millions of light years, but we can barely see through the dust clouds that obscure our view of much of our own galaxy. And yet, in another sense, we know the Milky Way intimately. We've mapped its structure, traced its spiral arms, cataloged millions of its stars. We've measured its rotation, weighed its mass, calculated its age. We've discovered that it's just one of hundreds of billions of galaxies in the observable universe. And yet it's special, because it's ours. Because every human who has ever lived, every story ever told, every moment of joy and suffering and wonder happened here, in this galaxy, on a small rocky planet orbiting an average star in an unremarkable arm of the Milky Way. There's something humbling about knowing that the light from the center of our galaxy takes 26,000 years to reach us. When you look toward the constellation Sagittarius on a dark summer night, you're seeing the Milky Way's core as it was 26,000 years ago, long before recorded history, before agriculture, before humans had even left Africa to populate the rest of the world. The galaxy you're observing is ancient history, frozen in light that has been traveling through space for longer than civilization has existed. And this connects to something even more remarkable. about the nature of observation itself. When astronomers study distant parts of the galaxy, they're not just looking across space, they're looking back in time. A star 10,000 light-years away appears to us as it was 10,000 years ago. If it exploded as a supernova yesterday, we won't know for another 10,000 years. The galaxy we observe is a patchwork of different eras, all visible simultaneously, like looking at a city where every building shows a different decade of history. The Milky Way contains stellar nurseries where stars are being born at this very moment, though we won't see the light from those newborns for thousands of years. The Eagle Nebula, one of the most famous star-forming regions, is about 7,000 light-years away. The iconic pillars of creation photographed by the Hubble telescope might not even exist anymore. They could have been destroyed by a nearby supernova thousands of years ago, and we won't know until the light from that destruction finally reaches us. This leads us to understand something profound about the nature of the galaxy itself. It's not a static structure. It's constantly changing, constantly evolving, but on timescales so vast that human lifetimes can't perceive the motion. Stars are being born and dying. Gas clouds are collapsing and dispersing. Black holes are feeding and dormant, all in a slow cosmic ballet that takes millions of years to unfold. Consider the Orion Nebula, one of the closest star-forming regions to Earth, only about 1,300 light-years away. Inside that glowing cloud of gas, hundreds of baby stars are igniting, surrounded by disks of material that will eventually form planets. Some of those planetary systems might already exist, worlds circling young suns, still hot from their formation. And we're watching it happen, watching the birth of solar systems that might, billions of years from now, harbor their own forms of life. But star formation isn't evenly distributed across the galaxy. It happens primarily in the spiral arms, where gas is compressed by density waves. Between the arms, in the quieter regions where we happen to live, star formation is much rarer. Our sun was likely born in a spiral arm billions of years ago, in a stellar nursery similar to the Orion Nebula, surrounded by thousands of sibling stars. But over time, those siblings have drifted apart, dispersed throughout the galaxy by orbital mechanics and gravitational interactions. Somewhere out there, scattered among the 100 billion stars of the Milky Way, are dozens or hundreds of stars that formed from the same cloud as our sun. We just don't know which ones they are. Which brings us to something unexpected about stellar families. Stars aren't born alone. They form in clusters, sometimes containing thousands of stars all born from the same collapsing gas cloud. Young star clusters are spectacular, dense collections of bright blue stars that blaze intensely but briefly. But over time, these clusters gradually dissolve. Gravitational interactions fling stars out into the galaxy, and eventually, the cluster disperses completely. Our sun's birth cluster dissolved billions of years ago, its stars now scattered across vast distances, strangers to each other. And here's where it gets even more interesting. Some stars in the Milky Way are hypervelocity stars, rogues traveling so fast they're escaping the galaxy entirely. These stars, typically ejected by close encounters with the supermassive black hole at the galactic center, can reach speeds of 1,000 kilometers per second or more. They're leaving home, never to return, shooting out into the intergalactic void. In a few million years, they'll be between galaxies, alone in the darkness, with no galactic disk to call home. But most stars stay bound to the galaxy, following their orbits for billions of years. Red dwarf stars, the most common type in the Milky Way, burn their fuel so slowly that even the oldest ones, formed in the early days of the galaxy, are still shining today. And they'll continue shining for trillions of years to come. Long after our sun has died, long after every star massive enough to be visible to human eyes has burned out. In the far future, in the deep old age of the universe, red dwarfs will be the last stars still burning, the final embers of stellar fire in an increasingly dark cosmos. This connects to something profound about the life cycle of galaxies. The Milky Way is currently in its prime, actively forming stars, full of gas and dust to fuel future generations. But slowly, inevitably, it's running out of raw material. Every star that forms locks up some of the galaxy's gas. Some of that gas is returned when the star dies, but some is lost, blown out of the galaxy by supernova explosions or winds from massive stars. Eventually, billions of years from now, the Milky Way will have used up most of its star-forming material. New stars will become increasingly rare. The galaxy will age. And alongside this slow aging, there's another process at work: stellar death. Massive stars live fast and die young, exploding as supernovas after only a few million years. Medium-sized stars like our Sun live for about 10 billion years, then swell into red giants before gently puffing off their outer layers and leaving behind dense white dwarf cores. The smallest stars, the red dwarfs, will outlive everything else. The Milky Way is slowly transitioning from a galaxy dominated by bright, massive stars to one dominated by dim, long-lived dwarfs and the remnants of dead stars. But let's shift our attention to something more immediate: the structure of the galactic disk itself. If you could somehow accelerate time and watch the Milky Way from above over millions of years, you'd see the spiral arms moving through the disk like waves, not rigid structures. Individual stars and gas clouds move in and out of the arms as they orbit the galactic center. The arms persist because they're density waves, regions where orbital mechanics cause matter to temporarily bunch together. This reveals something unexpected about our place in the galaxy. We're not permanently in the Orion Spur. Our solar system moves in and out of spiral arm regions as we complete our 200 million year orbit. Sometimes we're in denser regions, with more nearby stars and more frequent supernovas. Sometimes we're in quieter regions between the arms. This variation might have influenced Earth's climate and biology over geological time, though the evidence remains uncertain. The Milky Way's disk is only about 1,000 light-years thick on average, but it extends 100,000 light-years from edge to edge. It's extraordinarily flat, like a dinner plate, but it's not perfectly flat. It's warped at the edges, like a vinyl record that's been left in the sun. This warping is probably caused by gravitational interactions with satellite galaxies orbiting around the Milky Way, their gravity tugging on the disk and distorting its shape. And surrounding the disk is the galactic halo, a roughly spherical region containing globular clusters, ancient groups of stars that orbit the galaxy in elliptical paths that take them far above and below the galactic plane. These globular clusters are some of the oldest structures in the galaxy, containing stars that formed more than 12 billion years ago. They're stellar fossils, windows into the early history of the Milky Way, which brings us to understand something about the galaxy's formation. The Milky Way didn't spring into existence fully formed. It grew gradually, starting from a massive cloud of primordial gas that collapsed under its own gravity about 13.6 billion years ago. The first stars that formed were different from stars today. They contained almost no heavy elements, just hydrogen and helium from the Big Bang. Those ancient stars have long since died, but their descendants, enriched with the heavy elements they produced, still exist in the galactic halo. The disk formed later, as gas that hadn't yet formed stars settled into a rotating plane. This is why stars in the halo are older than stars in the disk. They formed earlier, before the galaxy's structure fully developed. The Milky Way is, in a sense, an archaeological site, with different populations of stars recording different eras of galactic history. There are structures within the galaxy that tell stories of ancient collisions. The Gaia Enceladus stream, discovered by the European Space Agency's Gaia satellite, is a group of stars with unusual orbits. They're moving in the opposite direction to most stars in the galaxy. These are the remnants of a dwarf galaxy that collided with the Milky Way about 10 billion years ago. Its stars scattered throughout our galaxy, but still betraying their foreign origin through their distinct motions. And this connects to a deeper truth about galactic evolution. Galaxies aren't isolated islands. They're part of a cosmic ecosystem, constantly interacting, merging, exchanging matter. The Milky Way has absorbed dozens of smaller galaxies throughout its history, each one adding its stars to our collection. In a sense, we're a composite, built from the remains of many smaller structures. The galaxy contains magnetic fields that thread through the space between stars, aligning dust grains and influencing the motion of charged particles. These fields aren't uniform. They're tangled and twisted by the turbulent motions of gas clouds and the rotation of the galaxy itself. When a massive star explodes as a supernova, it can inject energy into these magnetic fields, creating expanding bubbles hundreds of light years across. Consider for a moment the sheer amount of energy involved in galactic processes. A single supernova releases more energy in a few seconds than the Sun will produce in its entire 10 billion year lifetime. And supernovas are happening in the Milky Way every 50 years or so. Right now, somewhere in the galaxy, a massive star is in its final moments, its core collapsing, about to explode with unimaginable violence. We just don't know where or when. It might have already happened, and the light is still traveling toward us. The most recent supernova visible from Earth occurred in 1604, observed by Johannes Kepler. Before that, one in 1572, observed by Tycho Brahe. And before that, one in 1054 that created the Crab Nebula, recorded by Chinese and Arab astronomers. We're statistically overdue for another visible supernova in the Milky Way. Somewhere in the galaxy, a star is preparing to die spectacularly, and when it does, it will briefly become bright enough to be visible during the day, casting shadows at night. A new star in the sky that wasn't there before. Which leads us to consider the nature of the elements themselves. Every atom of carbon in your body was created inside a star through nuclear fusion. Every atom of oxygen you breathe was made in a dying star's core. The gold in jewelry, the uranium in nuclear reactors, even the iodine in your thyroid, all of these elements heavier than iron were created in the violent moments of supernova explosions. The galaxy is a forge, and stars are the hammers that pound out the elements of existence. The interstellar medium, the gas and dust between stars, is incredibly thin by earthly standards, but there's so much space that it adds up. The Milky Way contains about 10 billion solar masses of gas, enough to form 10 billion new stars if it could all be converted. but most of it won't be. Much of it is too hot or too diffuse to collapse into stars. It simply drifts through the galaxy, occasionally clumping into denser regions where star formation can occur. And that gas isn't static. It's in constant motion, stirred by stellar winds, supernova explosions, and the gravitational pull of spiral density waves. Some gas is falling toward the galactic center. Some is being blown out into the galactic halo. Some is simply circulating around the disk. It's a vast, complex fluid dynamics problem, operating on scales that make weather systems on Earth look trivial by comparison. There are molecular clouds in the Milky Way that are among the coldest places in the universe, only a few degrees above absolute zero. In these frigid environments, molecules can form and survive. Not just simple molecules like hydrogen and water, but complex organic compounds including amino acids, the building blocks of proteins. The galaxy is, in a very real sense, performing chemistry on a vast scale, creating the molecular precursors to life. This connects to something profound about our origins. The molecules that eventually became part of Earth, that became part of you, drifted through interstellar space as part of these clouds. They were irradiated by starlight, frozen and thawed, mixed and separated, long before the solar system even existed. You are made of atoms that have a history stretching back through billions of years of galactic wandering. The Milky Way has companions. More than 50 smaller galaxies orbit around it, caught in its gravitational embrace. The largest and most famous are the Large and Small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light. They're dwarf, irregular galaxies, each containing billions of stars, slowly orbiting the Milky Way. And as they orbit, our galaxy's gravity is pulling on them, distorting their shapes, stealing their gas. Eventually, they too will be absorbed, their stars becoming part of the Milky Way. But there's something unexpected about these satellite galaxies. They're distributed in a vast plane around the Milky Way, all orbiting in roughly the same direction. This isn't what simulations of galaxy formation predict. Satellites should be randomly distributed around their host galaxy. The fact that they're not suggests something about the Milky Way's formation that we don't yet understand. Even our home galaxy still holds mysteries. The center of the Milky Way is hidden from view, obscured by vast clouds of dust that block visible light. For most of human history, we couldn't see what lay at the heart of our galaxy. But in the 1930s, when radio astronomy was invented, everything changed. Radio waves can pass through dust clouds that block light, and suddenly, the galactic center revealed itself. A bright, complex region of intense radio emission, marking the location of that supermassive black hole and the dense clusters of stars surrounding it. Which brings us to understand something about the limitations of human perception. We evolved to see a narrow band of electromagnetic radiation we call visible light. But that's only a tiny fraction of what the universe is broadcasting. The Milky Way looks completely different in radio waves, in infrared, in X-rays, in gamma rays. Each wavelength reveals structures and processes invisible to human eyes. The galaxy we think we know is just one version, one slice of a far more complex reality. In infrared light, those dust clouds that block our view become transparent. And suddenly, we can see through them to the crowded stellar neighborhoods beyond. The galactic center becomes visible, packed with ancient red giant stars and young massive stars, all swirling around the central black hole. Some of these stars orbit so close to Sagittarius A star that they complete a full orbit in just a few years, whipping around the black hole at incredible speeds. their motion a testament to the immense gravity at the galaxy's heart. And here's where it gets even more interesting. The black hole at the center isn't smooth and spherical. Space-time itself is twisted and warped around it. Einstein's equations predict that a spinning black hole drags space-time along with it, creating a region called the ergosphere where nothing, not even light, can remain stationary. Sagittarius A's star is spinning, though we're not yet certain how fast, and that spin affects everything around it. This connects to something profound about the role of supermassive black holes in galaxy formation. Nearly every large galaxy has one at its center, and there seems to be a relationship between the mass of the black hole and the properties of the galaxy surrounding it. Somehow, these black holes and their host galaxies evolve together, each influencing the other's growth. The Milky Way and Sagittarius A star are bound together in a cosmic partnership that stretches back billions of years. But let's shift our attention to something quieter, more subtle. The Milky Way contains vast bubbles of hot gas extending above and below the galactic disk, stretching 25,000 light-years into space. These structures, called the Fermi bubbles, were only discovered in 2010. They glow in gamma rays, the most energetic form of light, and they're probably the remnants of a massive burst of activity from the central black hole millions of years ago. Even now, long after the event that created them, they continue expanding outward, a fossil record of the galaxy's violent past. There are rivers of stars flowing through the Milky Way, streams of stars that share common motion, marking the tidal remnants of dissolved star clusters and cannibalized dwarf galaxies. The Gaia spacecraft has mapped thousands of these streams, revealing the intricate structure of the galaxy's halo and the violent history of mergers and collisions that built the Milky Way we see today. Consider for a moment how we discovered all this. The Gaia mission measured the positions and motions of more than 1 billion stars with unprecedented precision, creating a three-dimensional map of the galaxy. For the first time in human history, we can see the Milky Way not as a static photograph, but as a dynamic system, with every star's motion tracked, every orbital path calculated. We're watching the galaxy breathe, watching it evolve in real time, though that real time unfolds over millions of years. And that mapping has revealed something unexpected. The Milky Way's disk isn't just warped, it's wobbling, precessing like a spinning top that's starting to tilt. This wobbling is probably caused by the ongoing interaction with satellite galaxies, their gravity tugging on the disk unevenly, causing it to nod up and down over hundreds of millions of years. The galaxy is far more dynamic than anyone suspected, which leads us to understand something about galactic archaeology. By studying the chemical composition and motions of stars, astronomers can reconstruct the history of the Milky Way, when it formed, how it grew, which smaller galaxies it absorbed, and when. Each star is a time capsule, its light carrying information about the conditions in the galaxy when it formed. Old stars have less iron and fewer heavy elements because the galaxy was younger, less chemically enriched. Young stars are richer in heavy elements, the products of countless generations of stellar death and rebirth. The oldest stars in the Milky Way are nearly as old as the universe itself, about 13.2 billion years. These ancient survivors are rare, hidden among the billions of younger stars. But when astronomers find them, they're like messages from the early universe. These stars formed when the galaxy was just beginning, when most of the heavy elements we take for granted didn't exist yet. Their atmospheres contain mostly hydrogen and helium, with only traces of heavier elements. And alongside these ancient stars, there are stellar corpses scattered throughout the galaxy. White dwarfs, neutron stars, and black holes, the remnants of dead stars. White dwarfs are common, dim embers about the size of Earth, but containing the mass of the Sun, so dense that a teaspoon of their matter would weigh several tons. They no longer generate energy through fusion. They simply glow from leftover heat, gradually cooling over billions of years. Neutron stars are even stranger. Formed in supernova explosions, when massive stars collapse, they're about the size of a city, but contain more mass than the Sun. Their matter is so compressed that atomic structure breaks down. Electrons and protons are crushed together into neutrons, creating matter so dense that a teaspoon would weigh as much as a mountain. Some neutron stars spin hundreds of times per second, beaming radiation like cosmic lighthouses. We call these pulsars, and they're scattered throughout the Milky Way. They're precisely timed pulses detectable across thousands of light years. And then there are stellar black holes, the final stage for the most massive stars. When a star more than about 20 times the mass of the Sun collapses, not even neutron degeneracy pressure can stop it. The core continues collapsing until it becomes a point of infinite density, a singularity, surrounded by an event horizon from which nothing can escape. The Milky Way probably contains about 100 million stellar black holes, most of them invisible, detectable only when they're actively feeding on nearby matter, or when they're part of a binary system with a visible companion star. This connects to something profound about the life cycle of matter in the galaxy. Nothing is truly destroyed. It's only transformed. A massive star explodes, but its core becomes a neutron star or black hole. Its outer layers are scattered into space, enriching the interstellar medium with heavy elements. Those elements become part of new gas clouds, which collapse to form new stars, which eventually die and scatter their matter again. The galaxy is an eternal cycle of transformation, matter endlessly recycled through different forms. There are regions in the Milky Way where this cycle is accelerated. Massive stellar nurseries where hundreds of stars are being born simultaneously. Many of them so massive, they'll live only a few million years before exploding. These stellar nurseries are violent places, filled with intense ultraviolet radiation and powerful stellar winds that sculpt the surrounding gas into fantastic shapes. The radiation from young, massive stars ionizes the gas around them, making it glow in brilliant reds and blues, creating the spectacular nebulas that grace astronomy photographs. But most star formation in the galaxy happens more quietly, in smaller clouds that produce mostly low-mass stars, red dwarfs and stars like our Sun. These stars will live for billions of years, providing stable environments where planets can form, and perhaps where life can evolve. The galaxy creates far more of these quiet, long-lived stars than it does massive, short-lived ones. It's as if the universe prefers stability to spectacle. Which brings us to consider the future of the Milky Way. 4.5 billion years from now, when Andromeda arrives, the collision will be spectacular, but strangely gentle. The two galaxies will pass through each other, their stars so far apart that almost none will collide. But their gas clouds will crash together, compressed by the collision, triggering enormous bursts of star formation. The night sky, if Earth still has observers, will be filled with brilliant new stars, thousands of them, lighting up regions that were dark before. The galaxies will separate, then fall back together, pass through each other again. Each passage will create new tidal streams, pulling stars out into long filaments that wrap around both galaxies. Over billions of years, through multiple collisions, the two spiral galaxies will merge completely, their stars mixed together, their gas clouds depleted by furious star formation, until finally they settle into a single elliptical galaxy. A smooth, featureless blob of stars with no spiral structure, no active star formation. Just billions of aging stars slowly orbiting a combined supermassive black hole at the center. And that merged galaxy will continue evolving. Its gas will be almost entirely used up. New star formation will become extremely rare. The massive stars will all have died, leaving only medium and low-mass stars. Over trillions of years, even these will age. The galaxy will slowly dim as more and more stars exhaust their fuel and fade to black dwarfs, neutron stars, and black holes. Eventually, in the deep future of the universe, the galaxy will be mostly dark, a ghost of its former self. But that's so far in the future, it barely seems real. For now, the Milky Way is vibrant, alive, filled with light and activity. Stars are being born, planets are forming, perhaps even civilizations are arising on distant worlds, looking up at their own night sky and wondering if they're alone. The galaxy has given us everything. The atoms in our bodies, the energy that powers our sun, the stable environment that allowed life to evolve, the elements we use to build our technology, even the night sky that inspired our ancestors to wonder and explore. We are children of the Milky Way in the most literal sense, made from its matter, shaped by its history, entirely dependent on its continued existence. And yet, for all we've learned, the galaxy remains mysterious. We don't know what dark matter is, that invisible substance that makes up most of the galaxy's mass. We don't know if we're alone, or if other civilizations are out there among the billions of stars. We don't know exactly how the Milky Way formed, or how many smaller galaxies it has absorbed, or what its earliest years were like. We're still learning, still discovering, still piecing together the story of our cosmic home. There are gas clouds in the Milky Way larger than entire solar systems, containing enough matter to form thousands of stars. There are regions where magnetic fields are so strong they can strip planets of their atmospheres. There are areas where space-time itself is bent by powerful gravitational fields. There are ancient stars older than most galaxies, and young stars still forming today. There are planets orbiting two suns, and planets drifting alone through the darkness between stars, ejected from their home systems by gravitational interactions. The diversity of the galaxy is staggering. No two star systems are exactly alike. Each one is a unique combination of circumstances: the mass of the star, the composition of its planets, the architecture of its orbits, its location in the galaxy, its history of impacts and near misses. And we've only begun to explore this diversity. Of the billions of star systems in the Milky Way, we've visited exactly one, our own. We've studied a few thousand others from a distance, detecting their planets through subtle wobbles in starlight or tiny dips in brightness. The rest remain unknown, unexplored, waiting, which connects to something profound about the nature of knowledge itself. Everything we know about the Milky Way, we've learned from here, from this one planet orbiting this one star. We've never left our tiny corner of the galaxy. Our most distant spacecraft, Voyager 1, launched in 1977, has only just barely left the solar system. It would take 75,000 years to reach the nearest star at its current speed. The galaxy is vast beyond human comprehension, and yet we've managed to map its structure, measure its mass, calculate its age, understand its evolution, all from this single vantage point. The light from distant stars in the Milky Way has been traveling for so long that the constellations we see in the night sky would look completely different if we could somehow view them from those stars' perspectives. The patterns we recognize, Orion, the Big Dipper, Cassiopeia, are accidents of our specific location in space and time. Move a few thousand light years in any direction, and the familiar shapes disappear, replaced by entirely new patterns that ancient humans never saw and never named. And this connects to something deeper about the nature of perspective itself. The Milky Way doesn't have an objective appearance. It looks different from every vantage point. From Earth, we see it edge on as a band of light. From above, it would appear as a magnificent spiral. From Andromeda, 2.5 million light-years away, it's just a small smudge of light, one galaxy among billions visible in that distant night sky. There is no single true view of the galaxy, only countless perspectives, each equally valid. Which brings us to consider the cosmic web, the large-scale structure of the universe. The Milky Way isn't randomly positioned in space. It's part of a small cluster of galaxies called the Local Group, which includes Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. And the Local Group itself is part of a larger structure called the Virgo Supercluster, a collection of thousands of galaxies spanning 110 million light-years. And even that supercluster is part of an even larger structure called Laniakea, a gravitationally bound region containing 100,000 galaxies. The universe is organized into a vast cosmic web of filaments and voids. Long strings of galaxies connected like neural pathways, surrounding enormous empty regions where almost nothing exists. The Milky Way sits on one of these filaments, connected to other galaxies through invisible threads of dark matter and gravity. We're not isolated. We're part of a vast network that extends across the observable universe. And that network is expanding. The universe itself is growing larger, space expanding between galaxy clusters, carrying them apart at ever-increasing speeds. Distant galaxies are receding from us faster than light, not because they're moving through space that quickly, but because space itself is stretching. Eventually, billions of years from now, the expansion will carry distant galaxies beyond our cosmic horizon. Their light will never reach us, no matter how long we wait. The observable universe will slowly shrink, and future astronomers in a distant galaxy might never know that places like the Milky Way existed. But for now, we can still see the echoes of the Big Bang itself. The cosmic microwave background radiation fills the entire universe, the cooled remnant of the intense heat from the universe's first moments. When you tune a television to static, about 1% of that static is actually this ancient radiation, the afterglow of creation itself, reaching across 13.8 billion years to touch your antenna. The Milky Way, like everything else, is bathed in this faint glow, this whisper from the beginning of time. The galaxy contains structures we're only beginning to understand. There are stellar streams too faint to see with the naked eye, but revealed by careful analysis of star motions. There are gas clouds moving at anomalous velocities, suggesting they were ejected from the galactic center by some ancient explosion. There are gaps and holes in the spiral arms where something, perhaps a close encounter with a satellite galaxy, disrupted the normal flow of stars and gas. Consider the complexity of modeling all this. To truly simulate the Milky Way would require tracking the motion and evolution of hundreds of billions of stars, accounting for their gravitational interactions, the behavior of gas clouds, the influence of dark matter, the effects of magnetic fields, the feedback from supernovas and stellar winds. It's one of the most computationally challenging problems in all of science. Current simulations can approximate galactic evolution, but they're still simplified models, missing much of the complexity that makes real galaxies like the Milky Way so intricate. And yet, despite that complexity, there are patterns, regularities, laws that govern how galaxies behave. The rotation curves follow predictable shapes. The relationship between black hole mass and galaxy properties holds across billions of light years. Star formation rates follow statistical distributions. The universe, for all its apparent chaos, operates according to fundamental principles that we're gradually learning to understand. Which brings us to something profound about the nature of physical law itself. The same forces that govern atoms also govern galaxies. Gravity works the same way in the galactic center as it does on Earth. Nuclear fusion in distant stars follows the same quantum mechanical rules as fusion in our Sun. The universe is unified, one set of laws operating at every scale, from the smallest subatomic particles to the largest structures imaginable. The Milky Way isn't separate from the rest of physics. It's a manifestation of those fundamental principles, operating over billions of years and vast distances. There are regions in the Milky Way where time passes differently. Near the supermassive black hole at the galactic center, where gravity is strongest, time runs slower than it does here on Earth. It's an effect predicted by Einstein's general relativity. The stronger the gravitational field, the more time dilates. The difference is tiny, but real. A clock near Sagittarius A star would tick slightly slower than an identical clock on Earth. If you could somehow spend a year orbiting close to that black hole and then return to Earth, you'd find that more time had passed here than you experienced there. And this connects to something even stranger about black holes. When matter falls into a black hole, from the perspective of a distant observer, it never quite crosses the event horizon. Time dilation becomes so extreme that the falling matter appears to slow down, approaching the event horizon but never reaching it, frozen in time. From the perspective of the falling matter, however, it crosses the horizon in finite time and continues falling toward the singularity. Two different perspectives, both correct, impossible to reconcile except through the mathematics of relativity. The galaxy is filled with paradoxes like this. Situations where intuition fails and only the equations can guide us. Quantum mechanics tells us that particles can be in multiple states simultaneously until observed. Relativity tells us that simultaneity itself is observer-dependent, that events that appear simultaneous to one observer might not be to another, moving at a different speed. The more deeply we probe the nature of the galaxy, the more we find that reality is stranger than we ever imagined. But let's return to something more tangible, more immediate. The Milky Way has a smell. Well, not exactly. There's no air in space to carry odors. But if you could somehow gather the organic molecules floating in the interstellar medium and smell them, they would smell like rum and raspberries. This isn't a poetic metaphor, it's chemistry. The molecule ethyl formate, which gives rum its distinctive smell and raspberries their flavor, has been detected in gas clouds near the center of the galaxy. Space smells like a tropical drink. There are stranger molecules out there too. Astronomers have detected ammonia, methanol, vinyl alcohol, even amino acids in interstellar space. The galaxy is performing organic chemistry on a vast scale, creating complex carbon-based molecules in the cold vacuum between stars. Some of these molecules eventually find their way to planets, delivered by comets and asteroids, potentially providing the building blocks for life. In a sense, the galaxy itself is involved in the process of creating life, preparing the ingredients that allow biology to emerge, which raises profound questions about the prevalence of life in the universe. If the raw materials for life are scattered throughout the galaxy, if every star system receives a steady rain of organic molecules from space, then perhaps life isn't rare. Perhaps it's common, even inevitable, given enough time and the right conditions. We simply don't know yet. We've found only one example of life, here on Earth, and we can't say whether it's typical or extraordinary. The search for extraterrestrial intelligence continues. Radio telescopes scan the sky, listening for signals that might indicate technological civilizations. Optical telescopes search for laser pulses or other artificial signs. So far, we've heard nothing but silence, the great cosmic quiet. But the Milky Way is vast, and we've only just begun to search. It's entirely possible that other civilizations are out there, perhaps listening for us just as we're listening for them. All of us isolated by the immense distances, unable to bridge the gulf between stars. Or perhaps we're alone. Perhaps life is extraordinarily rare, the product of an unlikely series of fortunate accidents that may never be repeated elsewhere in the galaxy. Perhaps intelligence is even rarer, requiring not just life, but billions of years of stable conditions, precisely the right environment, countless evolutionary paths converging on consciousness. If that's true, then we're uniquely privileged, the universe's way of knowing itself, the only conscious observers in all the Milky Way. Both possibilities are profound. If we're not alone, then the galaxy is filled with wonder beyond anything we've imagined. Alien civilizations with their own histories, their own art, their own ways of understanding the universe. If we are alone, then we carry an enormous responsibility to preserve ourselves, to spread beyond our fragile planet, to ensure that consciousness doesn't vanish from the galaxy. Either way, the implications are staggering. The Milky Way will continue long after humanity is gone. Whether we destroy ourselves or evolve into something beyond recognition, or spread to the stars and flourish for millions of years, eventually our time will end. But the galaxy will persist. New stars will form from the remnants of old ones. Planets will coalesce from protoplanetary disks. Perhaps new forms of life will emerge, entirely different from us, asking the same questions we're asking now. Where did we come from? Are we alone? What does it all mean? And billions of years after that, when the Milky Way has merged with Andromeda, when most of the galaxy's gas has been exhausted, when star formation has nearly ceased, the galaxy will enter its long twilight. The brilliant blue-white stars will be gone, burned out long ago. The galaxy will be dominated by cool red dwarfs, dim but stable, slowly burning their fuel over trillions of years. And scattered among them will be the remnants: white dwarfs, neutron stars, black holes, the corpses of stars that once shone bright. Eventually, even the red dwarfs will exhaust their fuel. One by one, they'll cool and fade, joining the growing population of stellar remnants. The galaxy will become dark, a vast collection of dead stars orbiting a central black hole, bound together by gravity but no longer lit by fusion fire. And slowly, over timescales so vast they barely seem real, 10 to the 20th years, 10 to the 30th years, longer, even this structure will decay. Stars will be ejected from the galaxy by gravitational interactions. Others will spiral inward toward the central black hole. Eventually, only the black hole will remain, alone in the darkness. And then, after an inconceivably long time, even the black hole will evaporate through Hawking radiation, slowly losing mass until it finally disappears in a final burst of energy. And then, there will be nothing left of the Milky Way, except photons and particles scattered across an expanding universe. No trace of the 13 billion year history, no memory of the trillions of stars that once shone, no record of the worlds that orbited them or the life that may have flourished there. But that ending is so distant it might as well be forever. For now, for billions of years to come, the Milky Way remains, bright, dynamic, full of mystery and wonder. A river of light across the darkness, a city of stars scattered across space, a structure vast enough to contain all of human history and small enough to be just one among billions of galaxies in the observable universe. We are here, now, in this brief moment of cosmic time, when the galaxy is alive with starlight, when planets circle countless suns, when the conditions exist for consciousness to emerge and wonder at it all. We're witnesses to the Milky Way in its prime, and whether we realize it or not, we're connected to every part of it, made from its matter, shaped by its history, participants in its ongoing story. The galaxy has no purpose, no plan, no intention. It's simply what happens when vast clouds of gas collapse under gravity, when nuclear fusion ignites, when matter organizes itself according to physical law. And yet, in that purposelessness, there's profound beauty. The emergence of complexity from simplicity, order from chaos, consciousness from matter. The Milky Way created the conditions for understanding itself, and now, briefly, wonderfully, impossibly, it does. As you drift towards sleep, let yourself imagine the vast spiral turning slowly in the darkness. Billions of stars following their ancient orbits, each one a sun with its own story, its own worlds, its own unique configuration of matter and energy. Imagine the light from those distant stars traveling across thousands of years to reach this moment, this place, your eyes. Imagine the atoms in your body, forged in stellar furnaces, scattered by supernova explosions, gathered by gravity into planets, and eventually into you. You're not separate from the galaxy. You're part of it, a small eddy in the vast cosmic stream. And that connection persists whether you're aware of it or not. The Milky Way continues spinning through space, carrying you along with it, a passenger on a journey that began before you were born and will continue long after you're gone. For this brief moment, you're here, conscious, aware, able to contemplate the immensity of it all. That's remarkable enough. Rest now, knowing you're held in the gentle grip of gravity. orbiting the galactic center along with hundreds of billions of other stars. All of us bound together in this ancient dance, this temporary gathering of matter that we call home. The Milky Way will be here tomorrow, and for billions of tomorrows after that, quietly turning, endlessly mysterious, forever beautiful. Good night.